So the first question that we have is what is the total charge, which we're going to talk soon about what is the total charge of A, and the reason I do here a dash, I do here a blank line, is because I want to each time to put a different thing here, and we're going to understand how to deal with this specific shape and find what is the total charge. But in the first example, it's going to be string. So let's draw a string, okay? Really careful, let's be careful with it. So the first thing of a string, what we need, it's just a line, right? Here it is. This is my string. It starts in some location. And let's put an x-axis. X-axis is like a meter, right? I can put it, like let's put the x-axis, right? Here it is the x. And we're gonna say that this one ends at location L, which is the length of the string. And somebody came to this particular string and start to put charge, okay? Some put charge. Here a little bit, here more, here more, here more. So I want to give you the function. Where is my pencil? Here it is. So I want to give you what is the charge density on this, how we put the charge. So we're gonna do as lambda x. In each location x, there's some different charge, so the idea is function. Some constant, doesn't really interesting, just lambda node, we're divided by the length square, but multiply by x squared. So what does it mean? It means that the charge is like a parabola. Right here, let's do, this is how much charge I have. Right, here it is. How much charge do I have here? So this is gonna be lambda as function of x. Here in this specific location, if I'm gonna use this equation, I know it's lambda node. So what we wanna know is what is the total charge. If I'm doing that, I'm gonna give you a really simple equation, which is the first equation you're gonna use in this class, which is the whole equal to the sum of its parts. What do I mean by saying that? So let's give it, we write it in English, let's write it in math. So the total charge that I have here, Q total, equal to what? To the sum, right? I have here sum of its parts. This is a part. This is, let's put it here. This is a small chunk, you see, small chunk with charge. So if I'm gonna sum all the small chunks of charge, I would know what is the total charge, which is a pretty basic idea when you think about it, but it's gonna be super helpful and useful here in this class. Okay, so how I'm gonna divide this string. So when I look at a string, like I don't know, like a sausage or string, what I think about it is cut it here, like this, tack, 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 tack. I'm just gonna cut it to small pieces like this. And I can cut it in many different sizes. If this is a meter, right? So I can cut it to centimeters, like this meter. And I can cut it to maybe millimeters, and it's gonna be better. Why it's gonna be better? Because if I'm gonna talk about centimeter, I can say what's going on here, but I need to move centimeter to tell you what's going on here. But if it's gonna be millimeter, it's gonna be really, really tiny. I can talk about each place really specifically. And what is better than millimeters? It's actually taking the limit. Okay, let's do here. Let's say that it's so small. It's the smallest thing you can. It's the smallest thing you can think about it. It's dx. It's infinitesimally small. Okay, so the length of each chunk that I have, I'm gonna use this one so you can see it in your eyes. But let's say that each piece, see here, each piece here, maybe let's do a random piece. This piece, okay, this one I take it out, up. Its length is dx. That's the idea. So let's go back to the charge density that I have here, this function. I'm gonna clean this one. The unit of the charge density, I didn't tell you, but it's Coulomb. It's not charge, it's C, but it stands for Coulomb per meter, which means on every meter I have this amount of charge. This charge, I have it per this meter. That's the idea of the unit, okay? So how I can find this dq? I want to find the sum of its part. But you know what, before that I want to say what we need to do. In each question, it's the same thing to do. The first thing we need to do is divide. I want to divide the object that we have. In this example, it's a string. So we're going to divide the string into small pieces. We already decide to divide it to sum the x length. And the second thing is to obtain. I want you to obtain this integral, okay? Obtain this integral. If you're going to do these two steps, you're going to do just fine, okay? So let's continue. So we divided already. Now let's say what is dq. So dq is equal to lambda x multiplied by dx. Why it's true? What is the unit of dx? It's meters, right? So this is gonna vanish with this, and what to stay with? Only charge. So this is great for me. So it actually makes sense. And this piece has some charge. I want this charge. This is the charge that we have. Okay, so this charge is actually 0 over L squared multiplied by x squared multiplied by dx. Perfect. I found dq. I finished the first step. I divided the whole thing to a small piece of charge. And right now I want to obtain this integral that I wrote here before, which is q tot equal to integral on dq, and this dq is this. So it's 0 over L squared x squared dx integral. And let's talk a little bit about the limits of the integral. Is this string is everywhere, all the place, or it starts in some location of x and end up in some other location? So it's actually start at 0 and end up at L, right? So it's not all over the world. We need to take care of this one. So perfect. So we have also boundaries. This constant, I can use my fishing rod, take it and pull it outside of the integral. So it's lambda 0 over L squared integral 0 to L of x squared dx. This is a polynomial, so it's really easy to solve it. So f as L squared x to the third over 3. The boundaries are this. So the final solution is square L to the third over 3. This one can go with this one, and we have the node L over 3. Perfect. So this is the solution. This is the total charge that I have on this string. How you can think about the charge density? You can think about this lambda, the charge density, maybe like an orange tree. Think about that you want to know this is not a string, this is maybe a trail, and the end of the trail is really close to some lake. And the orange density is depending on the trees, how many trees that you have. So here you have a lot of trees because you're close to the lake, and here you almost have none, you're really far away. And this is the concentration of how many trees that you have along the way. So if you want to know how many trees that you have, oranges that you have, so you need to know in each area what's going on. And that's what we did. We actually take this part and divide it to small chunks, and we knew what is in each chunk, what is the charge density, how many orange that you have inside each one of them, and we sum them all up. We sum all the trees that we have along the trails and count it. And this is the result that we have. So the next question gonna be the same idea, but we're gonna change this one. So follow along, let's continue to the next question.